Now we are going to talk about de Broglie waves. So basically, it started from the end of the 19th century when light was regarded as a wave and the matter as a collection of particles. Just as the light was found to have particle characteristics in terms of photons, matter proved to have wave characteristics. And the wave nature of the matter allows us to use electrons for constructing images like an electron microscope. So afterwards, de Broglie hypothesized from an argument from the symmetry in physics that the relationship E is equal to h nu and P is equal to h upon lambda or photons also apply on electrons. Thus, electrons should have wave characteristics, and de Broglie further the hypothesis of this de Broglie was further confirmed by the experiment of Davison and Germer that electrons undergo diffraction when interacting with crystalline matter, just like the experiment. So this is the experiment that was devised by Davison and Germer. This is an electron cathode element. The electrons are emitted by this cathode ray tube and are focused on a nickel target and are diffracted from the nickel target. So this diffraction is in agreement with the Bragg's law. Later it was found, the data confirmed that this is an agreement with the Bragg's law, and consequently the electrons were confirmed to have wave characteristics. Then the kinetic energy of the non-relativistic particle is given as half mv square, and we convert this mv into momentum, which is p square by 2m. P is equal to h by lambda quantum mechanically. So lambda is equal to h upon mv, and this is called the de Broglie wavelength. And if we accelerate the electron through a potential difference V, it gains energy E into this potential difference V, EV. And this energy, as we have seen, is equal to P square by 2m. So we equate this and the momentum comes out to be under root 2 MeV, which is equal to h by lambda from this equation 2. And further processing this, the wavelength comes out to be h upon under root 2 MeV. This is the wavelength of the electron emitted by applying a potential capital V. Now, if we consider the diffraction experiment, an electron is accelerated by a potential difference of 54 volt, and a maximum in the diffraction pattern occurs at 50-degree X-ray diffraction shows that the atomic spacing in the target is 2.18 in 10 to the minus 10 meter. So the wavelength through the formula h upon under root 2 MeV comes out to be 0.17 nanometer. And alternatively, when we confirm this with the Bragg's formula, the wavelength also comes out to be nearly 0.17 nanometers. So both these approaches are in agreement. So the de Broglie's hypothesis was confirmed, and this is a support. This is in support to the de Broglie hypothesis. And higher energy would yield a smaller wavelength for the electron, which suggests that the electrons probes for imaging at higher resolution. If we consider an electron microscope where these electron beams are used for imaging, after diffraction, they form the pattern on the screen. If we consider the atomic line spectra of elements, we see that the spectra is not a continuous one. We are not getting the continuous bands like they should be ideally, like in the case of white light, they are. But if they are emitted by the characteristics of an element, they are discrete values. Like they have selected values of lambda for violet, subtrate. Well, you're not going to get a continuous spectrum. There are certain specific wavelengths that you are going to get, not all. Afterwards, Rutherford planned his experiment of bombarding the gold foil by an alpha uh, particle. And ideally, as per the Thomson model, where he considered that the electron, the positive particles are flowing inside the atom in the negatively charged fluid. So according to this model, the electron, the beta gamma ray particles, the alpha particles of the incident ray should pass undeviated from, but they were found to be scattered or diffracted, which is only possible when we have something high dense body inside the center. So it was concluded that the nucleus is a positively charged body inside the center and the electron revolves in orbits. And the minimum kinetic energy of these electrons can be calculated using this formula. So Rutherford suggested that the electrons revolve around the new positively charged nucleus. But as we know that while moving or while accelerating or orbiting around the nucleus, the electron will emit electromagnetic radiation and its energy will get deteriorated, and consequently it will come to a point that it will after losing energy it will start going towards the nucleus, and at a certain instant its energy will be so much less that it will go inside the nucleus. But that this doesn't happen. So later on, Bohr came up with this theory of hydrogen or hydrogen-like atoms, that an electron move in orbits around the nucleus, and those have, if orbits are only possible, whose angular momentum is an integral multiple of h upon 2 pi. So if an electron is moving in a higher orbit, it will emit a photon and will jump to the lower orbit, and the energy will be transferred to the photon. And if the electron is moving in a lower orbit, it can absorb energy from a photon and move to the higher orbit. The energy absorbed is the energy difference between the two levels. And moreover, it was observed that either absorption or emission between the two specific levels, the same wavelength was emitted. That means the photon, the amount of energy that a photon is emitted or absorbed is same. So the main postulate of the Bohr theory was that the nth allowed orbit, the electron has a quantized orbital angular momentum of nh upon 2 pi. And for a circular orbit, the magnitude of the momentum of this nth orbit is n into h cross. One way to get a physical intuition about the quantized nature of the atomic orbits is to consider the wavelength of an electron in various orbits as lambda upon hmvn, where v is the velocity in a particular orbit, nth orbit. And when this is balanced, the forces are balanced, we get the Bohr's result. And we see that for each Bohr orbit, the radius is different, we will have a different wavelength. So the wavelength is different when the photon is, it depends on the level from which it is emitted. Since the electrostatic force must supply the centripetal force to keep the electron in a circular orbit, you can see that both the forces, the central seeking force and the force, those should balance to keep the electron in the orbit. We see that the electrostatic force is this, and this is a centripetal force. They should be balanced. So from this, we can find the radius of the Bohr orbit in consideration, that is the radius of the nth orbit. And for the 0th orbit, it is called, this value is called the Bohr radius. As far as hydrogen atom is concerned, the line spectrum of the bottom of the slide is not of the entire spectrum of hydrogen, but it's just the visible light portion. So total energy is the sum of the kinetic and the potential energy, and the wavelength of the emitted radiation is equal to a constant called the Rydberg constant multiplied by 1 upon the lower level square minus 1 upon the upper level square. We see from this that when there is a transition from higher levels to n is equal to 1, the series emitted is called Lyman series. When there is a transition from higher levels to n is equal to 2, it is Balmer series. When there is a transition from higher levels to n is equal to 3 is Preston series. When the transition takes place from higher series to n is equal to 4, it's Brackett series. And when it is n is equal to 5, it is Pond series. So basically, we have Lyman, Barman, Paschen, Brackett, and Pond series. Here we can see that the spectrum is discrete, not a continuous one. So this theory is applicable to hydrogen and hydrogen-like atoms. All the bound energies are negative and approaches zero as n gets larger. And here all the energy levels for hydrogen and singly ionized helium. The simple picture does not work for atoms with more than one electron. And here we have not taken into account the finite mass of the nucleus. And to correct this, we should use the reduced mass in place of the electron mass. So now we have three processes: absorption and emission. And emission is of two types: spontaneous emission and stimulated emission. So absorption will take place when a photon is incident, and the absorbing that photon, the electron will move from a lower to a higher orbit. The emission will take place when the electron will come from a higher orbit to a lower orbit emitting a photon. And if a photon is incident and it excites the transition from the higher level to a lower level and consequently two photons are emitted, it is a stimulated emission. So here this is related to the temperature. So thus we saw how the dual nature behaves and what the de Broglie postulated and how it is related to the Bohr concept and how Bohr was able to explain the fine structure in the hydrogen line spectra and other elements similar to the hydrogen one, basically hydrogen and helium. So today we stop here. Thank you.